Okay, hello everyone. Thank you for coming. My name is Xiaojing Teng. I'm currently an assistant professor at James Madison University. Today, I'm going to walk you through my chapter, which is A3.5, Deforestation Viewed from Multiple Sensors. So this is one of the application chapters, specifically in the terrestrial applications. This one looks at how we can detect deforestation by combining data that is collected from different sensors. Specifically, we will look at Landsat, Sentinel-2, and Sentinel-1. So I'll break down this presentation into three sections. There will be a chapter overview, looking at what we'll do with this chapter, and then I will explain the theory behind the chapter a little bit, how we are actually going to do it, kind of the remote sensing principles of how we can combine these sensors to detect change faster. And then we'll go into the specifics of the lab and focusing on the code and how we actually implement these things. Okay, so starting with the chapter overview, the goal is to demonstrate a very simple method of how to combine data from Landsat, Sentinel-2, and Sentinel-1 to monitor tropical forest disturbance. And what we'll learn is how we can try to combine optical and radar remote sensing images for change detection, how we can fit a time series model to time series data that is presented as a image collection, how we can use the time series model then to detect any anomalies in the newly collected image as an indicator of changes that's happening on the ground, and how we can perform the change detection and actually create a map of these changes. Now, this chapter is designed for advanced users. It kind of assumes that you already went through all of the fundamental chapters. So it assumes that you know how to import and pre-process large quantities of Landsat, Sentinel-2, and then Sentinel-1 data as image collections. If you're not there, that's okay. You can still welcome to enjoy this presentation because I will talk about sort of fundamentals of the concepts behind this model and how we do it. But I do encourage you to go through the fundamental chapters before you actually try this chapter. Okay, starting with the theory, why do we need to detect deforestation from multiple sensors? Well, for some of the issues in the tropics, such as illegal logging and encroachment on protected areas, we want to know when they are happening or where they're happening as soon as possible. And so we want to detect these changes as quick as we can as they are occurring in the tropical forests. Now, the main limiting factor of how fast we can detect these changes are often the observation frequency. If you're using optical data, such as Landsat and Sentinel-2 in the tropics, as you know, it's going to be extremely cloudy. And when it's cloudy, there's nothing we can do with the optical data. With SAR data, it's less of a problem. But the idea is that if we can combine all of the data that we get in this region, if we combine Sentinel-2, Sentinel-1, and Landsat together, then we have the potential to maximize the data density and therefore detect the change faster. So these are two figures that I pulled from my paper just to show you in this region, in the Amazon, we get a lot better data density if we try to combine the three sensors. And in this particular example, we can detect change a lot faster by combining the three sensors compared to using individual sensors. Okay, so I assume everybody know how to access the book. This is the link to access the code for the book. So if you click that link, or sometimes if you have to click the refresh button, you'll see the repository show up. And if you go to one of the applications chapter, if you find A3.5, that will be the code to my chapter. And I have a few checkpoints where you can check if you are doing things correctly. So starting with the specifics, my chapter starts with sort of a demonstration of how this algorithm works. This is called the FNRT algorithm, stands for Fusion Near Real Time. So I use a little bit app to show you that. This is an app that is built by me just to show you conceptually how the algorithm works. I'm showing you visualization of changes, visualization of time series. I want to want you to get a feeling of how the things work. What do you see with Landsat data? What do you see with Sentinel-2 data? And what do you see when you're starting to combine the three? So let's actually go there. So this is the app. If you go to the checkpoint code for the first checkpoint, you'll see there's nothing in there. There's only a link to a to the app. So if you just copy that link to your browser, it will take you to this nice app. Now, there's a few components to the app. Let me quickly explain it. So there's a map area. You should be quite familiar with this, where you can see the locations, the background, high-resolution images, and also as well as anything that is added to by the app. Down here, you have something on the left, which is I call the time series panel, which basically will plot the time series of any point that you click in the map. And then on the right-hand side, you have a little bit control panel where you can do different things. Now, basically, there are three things you can do with this app. There's the fit button. When you click it, it will activate the fit time series model tool, where you can then click on anywhere in the map to get the time series from individual sensors. You can choose lens set, Sentinel-2 or Sentinel-1. This is for you to explore data from individual sensor, how it looks like as a time series, and then how the model looks like when we start fitting a harmonic model to the data. The second button is a monitor button, which will actually do the monitoring still over the time series data. So if you activate the monitor button and then click anywhere in the map, you will see the FNRT results where it's trying to start looking for the forest disturbance in near real time. And then in the monitor case, you can start to combine sensors. So there are checkbox where you can check different sensors you want to include in a monitoring process. And then lastly, there's a run button which will actually run the whole process over a small region and then create the map of disturbance in that region. So let me do a quick demonstration of the app. So here it is. I already clicked the run button, so I didn't want to wait for too long, so the map is already there. But let me turn it off. So this is how we start. What we start with. So if you activate the fit button, and then on the right-hand side, there's the select box. Let me start with lens set. So I want to just look at lens set data for one point. You just click somewhere in the map. The app will start thinking, and it will plot the lens set time series for the point I just clicked. You'll see the time series. You'll see the model fit. You'll also see the red points, which is the data, the new data in a monitoring period where we're trying to detect change. Now, this particular pixel that I click doesn't have enough change. So you can see the model corresponds pretty well with the data, and no change is flagged. Now, to do monitor, then we can use the monitor button down there. Now, on the right-hand side, you can choose which sensors you want to include. There's lens set, Sentinel-2, and Sentinel-1. Let's start with just lens set. So I'm going to use a little bit of help. I'm actually going to activate the map so I know where the disturbance are, because I want to click in the place where there's actually a change. So it's showing up in different colors that correspond to when the change happened. I'm going to click in this large patch where now there's a deforestation event going on. Now, the code is going to start thinking, and what you see plotted here are the change scores calculated for every image in our time series. Now, the change happened in the beginning of 2020, so you see the scores are mostly 0 in 2019 and 2018. You do see a few anomalies. These are usually missed cloud in the data, which the model is designed not to be fooled by these individual changes. Now, if you go to 2020, you'll see the score starting to explode into tens. That means the images that is coming in looks very different from the time series, initial time series model. So we're flagging these as changes. And as we see consecutive changes, then we will insert a break, which is the little blue dot over there. That's where when we actually confirm the change there. So we can start to include more sensors in the process, and you'll see we'll detect the change faster than using just one sensor because we have more data to work with. Let's just wait a few seconds. It should pop up momentarily. While we're waiting, there's the last thing is the run button. If you click that, it will run the whole algorithm over this entire area, which is a small test area, about 20 kilometers by 20 kilometers. This is my test area to demonstrate the lab. So you'll see the red box is the test area. And if you click the run button, you'll get a map of all of the forest disturbance in this area in the year of 2020. Now the time series is loaded. As you can see, we detect the change much faster. The green dot is showing up in January 27th because we have a higher density of the observation. We detect a change much faster. Now it's a little bit noisier in the training period. That's because we're including data from multiple sources, including the radar data from Sentinel-1, which tends to be a little bit noisy, but that's fine. We detect a change much faster, basically. So that's the quick demonstration of the app. This shows you sort of how this algorithm works, basically. The app is there for you to play with. You can try different sensors, you can try different combinations, rerun it. We can run it with Landsat, run it with Landsat and Sentinel-2 to see if changes show up as detected sooner. So this is basically there for you to explore the algorithm and how it works, kind of look at the results. Now let's go into specifics for the rest of this presentation. I'm going to go into specific, basically trying to show you how we get there, how you can do this all things with Google Earth Engine. So starting with section 2, we want to begin with defining a study area and defining a few model parameters. To define a study area, there's different ways you can do it. You can import a existing feature from a Earth Engine asset. You can just import, you can upload a shapefile to Earth Engine, and then you can import it from there. You can do it by just using the drawing tool in the code editor by drawing a box, or you can just create a polygon by entering the coordinates. So to do the demonstration, this is the study area that I use, basically a 20-kilometer by 20-kilometer box located in the Amazon. This is what I will use for the demonstration, but you're free to try it in another region by including your own study area. There are a few parameters that you can change that will basically, you can tune the model to be either more sensitive or more conservative. Let me actually go to the code. So as you can see, the top section, that's the study area. Basically, I created an object called test area using a EE geometry and polygon, entering the coordinates. Now you can do it in different ways, as I mentioned. A few parameters you can tune. You have to define a training period, which is usually a 3-year time period before your desired monitoring period. And then you can define your monitoring period. It's basically a time period that you want to look for changes. It can be a very recent time period. Now, we started designing this lab a few years ago, so that was why I was focusing on the year of 2020 for the demonstration, but you can do it for the year of 2023 to do more kind of near real-time changes. Now, there are a few parameters you can tune, as I mentioned, to make it more sensitive or to make it more conservative. I would suggest you read my paper before you start playing around with the parameters. For beginners and for first-time users of this algorithm, I would recommend that you just keep it as default. But these are a few things. Basically, if you detect too many changes, you have too much false positives, you can make it more conservative. If you're not detecting enough change, then you can sort of tweak it to be a little bit more sensitive. So checkpoint B, nothing really needs to be changed. If you click run, nothing will happen. These are just predefined parameters. So, okay, moving on. Let's go to section 3. So the first step is we need to load the data. So we need to load Landsat, Sentinel-2, Sentinel-1 data for both the training period and the monitoring period separately. Now, this chapter assumes you already know how to do this, how to do the pre-processing, how to apply the cloud mask to Landsat and Sentinel-2 data, how to do the pre-processing for Sentinel-1 data. If you don't, please go back to the other fundamental chapters about this. Now, I have included a few functions, a few utility functions in a separate script, which is also part of this book repository. In there's all of the function you need to pre-process the Landsat images and to create the image collection for the time series data ready for the next step. So for here, I won't talk about it in detail, but feel free to go to the utility script and learn from there about how we actually load the Landsat Sentinel-2, Sentinel-1 data and how we do the pre-processing there. To continue this lab, basically, we just import that script by requiring the location of that script, and then we are free to use all of the function that is already in there. So there's the load Landsat data function we can use. You just have to define the area and the time period. So we can use that to load the training data for Landsat and the monitoring data for Landsat. And then we do the same. There's a load S2 data function in the utility script here that can load Sentinel-2 time series, and it also just take the area and the time period. So we can use that to load the training data for Sentinel-2 and the monitoring data for Sentinel-2 as well. Same thing for Sentinel-1 data, we load the training and the monitoring data for Sentinel-1. Now, for the two optical data, Landsat and Sentinel-2, there is one extra step that we want to do, which is an in-mixing process, which will create a special index called NDFI, which is Normalized Difference Fraction Index, that really tracks canopy cover in the tropics really well. So if you want to learn more detail about NDFI, please go to the reference in the book, and it will take you to the paper that actually introduced this index. Basically, this index tracks forest canopy cover really well in the tropics, and that's why we're using it. Now, let's go to the script. The unmixing function is actually provided in the script. As you can go through, it takes a set of N members, including green vegetation, non-photosynthetic vegetation, soil, shade, and cloud. It will do the spectral unmixing using image.unmix function. And then from there, it will then calculate the index NDFI, and then it will add it back to the images. So this is the function to do it. Basically, we just apply that function on the data that is loaded. We only do it for the Landsat data and the Sentinel-2 data, because this is a function that can only be applied on optical data. So we just load the Sentinel-1 data. Now here, we already loaded everything. We're ready to do it. One extra thing we need is a forest mask, because we're detecting forest disturbance. So we want to focus our detection to forested areas. So here I'm utilizing the global forest change map from University of Maryland, Hansen's group. So this Hansen map, this is also available on the Earth Engine. So we load the tree cover for 2000. We add the loss and gains in the past 20 years. That's how we get a forest mask for 2020, basically the beginning of our monitoring period. And we will use that mask to look for just forested area to do our detection. Now that's there. Now here, if you do everything, and we can actually print out some of the time series data just to look at it, what the data structure looks like. On the right-hand side in the console, you can see if you run the code, everything got printed out. There's training data for Landsat, there's monitoring data for Landsat, and same thing, there's training and monitoring data for Sentinel-2 and Sentinel-1. One thing you will notice, we have a lot more Sentinel-2 data compared to Landsat, which is because we have basically two Sentinel-2 collecting data at the moment. And also Sentinel-2 is cut into smaller tiles. We're actually in a place where it's an overlapping zone between two tiles. So that kind of double the amount of data as well. You'll also notice that we have more images in the monitoring period, more images in the training period compared to the monitoring period. That's because the training period is 3 years, basically, and the monitoring period is only 1 year. So just a few things you can observe. In there, if you look at individual images, there are the spectral bands, there are the spectral unmixing bands, and also there's NDFI, which is the thing that we will use for the next step. So this is the first kind of the very first step where you actually load the data to do the before you can do any analysis. Okay, let's move on. So after we import and pre-process the data, so that the next step is do some training, do a time series model training. What we want to do is use the data for the training period to establish sort of the baseline time series model, which we can then use to detect change in the monitoring period. Now, the main function that you use to do it is basically this fit harmonic model function. What it does is it will fit a harmonic model to all of the data in the training period, and then it will calculate also the RMSE of the fitting, which we will use later to calculate the change score. Now, I won't go too much detail into this function. If you're interested, you can read the reference paper attached in the book, which will explain how the harmonic model works. But basically, it will fit a harmonic time series model to all of the data in the training period. So in the code, you'll notice in the checkpoint code, there is the out of the way. There is a few utility function that supports the fit harmonic model function. So toFrac year function basically will convert the date to a fraction year, which is used as the predicting variables. So it has to be a continuous variable. So we use fraction year here. And then the fit harmonic model function will fit the harmonic model. Okay, moving on to the slides. Once we complete the model fitting, the next step we want to do is actually save the model training model. The reason we do that is this is kind of a computationally heavy step. And if you want to do the whole process on the fly, like you're used to just running the script, it may actually break Earth Engine because it's just a very complicated process. So we want to break it into different steps. And here we're doing the training over 3 years of data. We want to save the results, run it in the background, save the results so we can use for the next step. So what we do here is we actually export the trained model to an asset. And we'll save all 3 assets into a same image collection. So we run the training separately on Landsat data, Sentinel-2 data, and Sentinel-1 data, and we want to save them, export them as 3 images in the assets into the same image collection. So what we do here is we will use this save model function, which will export everything to an image at a 30-meter resolution. So if you run the code, you'll see if you switch to the tasks tab, there are 3 new tasks posted. You have to actually run the task that will actually save the thing to an asset. Now, this will take something from 10 minutes to 20 minutes to run. So please be patient with that. We're not actually going to do it right here, but if you're doing it on your own, you have to wait till the job to be finished and before you have to move on to the next step. Now, if you're doing it for the same region that I'm testing this algorithm, which is this 20 kilometer by 20 kilometer box around in the Amazon, then you don't have to do this because I've already run these 3 tasks. I've already saved the results as an asset in the asset repository for the book. So it's there. Everybody have access to that. So we don't have to do it. But if you're doing it on your own, if you're doing it in a different region, you have to run this step. You have to actually export the asset. You have to run the task, and don't forget to do that. Okay, moving on to the next step. Let's assume we finish this step. We have the task finished and everything is saved. Now, of course, the next step, the first thing you do is we need to load it, right? We saved it in the image collection, so we need to load it back. Now, this is how you do it. You have to load the image collection. This is the default image collection, which is basically the trained time series model for Landsat, Sentinel-2, and Sentinel-1 time series over that small region that I use for demonstration. Again, if you do it in a different region, you have to run the tasks, save it in your own Google Earth Engine asset. So here you will have to modify the code, change this path to where you saved your assets. But to continue doing the lab using the demonstration region, then you can just load the model that I have already run. So here you can see we're filtering, we're loading the whole image collection, but we want to separate the time series model for Landsat, Sentinel-2, and Sentinel-1. So I'm doing a little bit of filtering here. I'm filtering based on the sensor to just get the Landsat one, Sentinel-1, Sentinel-2 one, and the Sentinel-1 one. So next step is we need to actually do some change detection, right? Before we can do change detection, there's a few metrics we want to calculate. So our change detection will be based on a metric I call the change score. The change score is a measurement of how new images differ from the model prediction. So the model prediction assumes there is no land cover change happening on the surface. It will just predict based on the prior data. So it's trying to just continue status quo. Nothing changed. What's the image going to look like based on the trained time series? Now we compare that predictive value to the actual images coming in, to the new images collected during the monitoring period. If they look fairly similar, they will have a very low change score, right? Because they're the same thing. Now, if something happened on the surface, some trees got cut down, there's actual forest disturbance on the surface, then the actual image will look very different from the predicted image, and it will have a very large change score. And we will use that as an indicator of changes. Now, there are several functions that we will use to calculate the change score. I won't go into too much detail of those. There's the D-array model, basically because the time series model training results is saved as an array image. Basically, array image allows you to save multiple variables in one band, which is efficient. But when we actually try to use it, we want to sort of expand it back to a multi-band image so we can actually properly read all of the model coefficients and use it for creating the prediction image. So that's what this function is doing. Second function we will use is create predict image function. This will take the model coefficients and then it can create a predict image given a date. So the date is the X basically, and then using all of the coefficients, it can calculate the Y, which is the NDFI for the optical image and the EV backscattering for the Sentinel-1 image. So that will create a whole new synthetic image, which is basically a prediction for any given date in the monitoring period based on the trained time series model. Now, the add predicted function will add the predicted image to the actual image that is coming in from for the monitoring period. Those are real images. Next step is we calculate something called residuals, or we use the add residuals function. The residual is basically the difference between the predicted and the actual image. And as you can imagine, if there's no change, the residuals will be fairly low. If there is a change on the surface, then the residual will start to get larger and larger. The last step is the change score. The change score is basically we're normalizing the residual based on the RMSE. So that will be a normalized value, which we can then put a threshold on to sort of turn that into change and no change. Okay, so these are the code to do it. Basically, you apply these functions that I just mentioned sequentially on the data over the monitoring period, and then you will get to the scores. And let's look at what it looks like. So we'll go to the code here. Close this. So here, as you can see, the top here, I'm loading the models, which is the thing that we saved as an asset. I'm loading it back here. That will be the trained time series. And you can see the D-array model function, the create predicted image function, the add predicted function. And here we're de-arraying all of the images. We're just basically applying these things sequentially, adding the predicted image to the images in the monitoring period. Now here I printed this out so you can actually see what the data structure looks like after these processes. So I'm printing out the lens set predicted image, which is created based on the time series model and also the monitoring, the image over the monitoring period, right? So if you remember, we have 31 image during the monitoring period from lens set. The monitoring period is the year of 2021. And then we created 31 predicted image as well that correspond to the 31 real images in the monitoring period. So here is what the LST predicted look like. So now you have still 31 images, but they only have two bands. They have the NDFI band, which is from the real image, which is what we use to do the detection, the metrics. And then you also have a predicted image, which is also NDFI, but that's from the model prediction. So it's the predicted image and the real image as two bands in the same image. So here. Now the next step is where we calculate score. So there's the add residuals function. There's the add change score function. So we apply them sequentially to the data to get the residual and also to get the change score here. And then we apply a threshold to the change score. Basically, we separate them into change and no change. And after this step, you'll see you get the scores object, which also has the same amount of image comparing to the predicted object. Basically, we're doing it over the same 31 images that we have for the monitoring period. And look at the structure of the data. You don't have the NDFI and the predict anymore. We have rather we have a band of the z-score, which is basically the residual scaled by the RMSE. And then we also have the strike image, which is basically when we apply the threshold to the change score, so we get the change and no change, kind of the binary layer for there. And we have it for all 31 images for the monitoring period. Now here I only printed out the results for the lens set. We do the same for the Sentinel-2, we do the same for the Sentinel-1. What we want to get is to get to the binary no change and no change layer for all three sensors, because they are different sensors. But if we can get to a metric that is normalized across sensors, that's when we can actually combine them together to form a denser time series and do the change detection over there. So that's what we are doing. We're getting to this binary change and no change layer for every image in the monitoring period. And these we consider them to be normalized across all three sensors, and we can do the combination. That will be the next step. So moving on to the next section is the multi-sensor data fusion and change detection. So basically what we do first is we have the change score, we have the change flags or the change and no change layer that is calculated from Landsat, Sentinel-2, and Sentinel-1. Here, I'm just merging them together because we're ready to combine them. They're kind of the change score, and then also the change flag is a normalized metrics across sensor where we can combine them. So I use the merge function to merge the three image collections. And then also I want to sort it by time because we're doing the change detection in a chronological order. We're looking for change over time, right? So that's what we did. That's what I'm doing here. Now, the change detection itself uses a function called monitor change. What it does, it will operate based on the binary values, so change, no change. Remember, we have that binary values over time combined together from all three sensors. What I do is I look for consecutive changes as a way to confirm changes. Remember, when we're looking at the time series, we notice there are mist cloud in the data that may show up as change. We want to avoid those, so we look for consecutive signal of change in the time series. What we're looking for here is 4 changes out of 5 observation monitoring windows. So 5 consecutive observation, if we see 4 changes in there, then it's a confirmed changes. So what this change monitor change function does is it will start with all negative. So assuming there's no change, so we'll start with 5 zeros. And then it will eliminate the oldest score because it doesn't matter anymore. We're moving along the time direction. We're starting from the earliest observation to the latest observation. So we're going in that temporal direction. So we take out the oldest observation and we add the next observation. So assuming the next observation is a change, so now we have a 1 in our kind of small monitoring window. Now, this is for every pixel. So we continue that process, right? We remove the last observation, we continue to add new observation. Now, at some point, if there's really a change to this pixel, we will see like multiple 1s in the little monitor window we're looking at. And as soon as we can see 4 changes within that 5 observation monitoring window, that's where we actually flag a forest disturbance. So this is how this function works. It will check every observation in the time series in the chronological order, and basically it's looking for 4 changes out of 5 observation window, and that's a indicator of a real change on the surface. Now, if you go back to sort of the very first step where we set the model parameters, this is the parameters you can tune. So you can look for 3 observation in the 5 window, or you can look for 3 observation in the 4 window. You can play around with that number. Basically, it will make the model either more sensitive or more conservative. So that's that. Okay, looking at the code checkpoint, there's the main thing here. The first step here is we created a fused time series where we combine the scores from Landsat, Sentinel-2, and Sentinel-1 using the merge function, and we sorted that giant image collection based on the time because we're looking at images in chronological order. The next step is the monitor change function. It's a slightly complicated function, but you can go through the code to sort of try to get a better understanding of it. But basically, it looks for 5 observations at a time. It will remove the oldest observation, add the new observation, and then it will check if there's enough change flagged within that monitoring window to detect changes. So we apply that over the entire fused time series that we have with the parameters, and then we apply the forest mask to it as well, because we want to limit our detection to forested area. What we get is the final object called alerts, which will be the forest disturbance alert for this area that you're doing. So move on to the next slide. So we also want to visualize the results here. So we're visualizing based on when the change is detected. So it's color-coded based on that. Red is earlier changes, blue is later changes, basically. And we can add it to the map, as you can see here. This results in this small section of the Amazon forest. These are the new forest disturbance that we have in this region, and they are color-coded by when they are detected in the time series. Now you see a few large patches. You also see a few noisy stuff out there. These are expected. What we often do is we apply a spatial filter to the results to throw out these smaller random speckles. That's usually a result of the speckles in the Sentinel-1 data. Now, I don't want to go too much detail into that because that gets into the realm of concept of radar remote sensing, but that's the idea as we're detecting these large patches of changes. Okay, so that's kind of the entire lab. Basically, you go through this process, combine data from Sentinel-1, 2, and 3, and then you flag force disturbance by using the combined fused time series of change flags. Now, one question that I get asked a lot is, how do I run this in a different region? You can. So what you do is when you go through the changes in the first section 2.1, where you define the study area, basically you just change it to another area of your own interest. But there is a few things you want to follow, because there's a lot of computation going on, sort of processing all of the data from Landsat, Sentinel-2, and Sentinel-1, doing the time series model fitting. So there is a lot of computation. You don't want to apply it to a very large area. It's not going to work. You'll run out of memory, and then you'll get an error. So try a smaller area. If you do want to apply it over a relatively larger area, do it over small tiles and then combine the results later. And also don't forget to run the save model function, and then also actually run the task. So you save the model time series model training results as an asset. And then in the next step, when you load them back, you want to modify the path to the image collection to where you save these things. Now, the default code for the lab applies this algorithm to this little test region in the Amazon that I selected. And then the default code for the lab will load the pre-saved model time series model result that I have already run and saved. So if you want to apply it in a different area, you will need to modify these things. And the other thing I want to mention is this code is supposed to be a simplified version of the original FNRT algorithm. It is meant to work as a lab, as a chapter to teach you how to combine data from different sensors to do monitoring of deforestation. It is not supposed to be an operational monitoring system where you use it to actually monitor deforestation over a very large area. This is a simplified version. A lot of things got simplified, and it's not optimized in a way that is really efficient to do over a large area. If you are interested in monitoring deforestation in real time over a large area, please refer back to my paper, which the link is posted in the book as well. So go to my paper of the FNRT algorithm. On there, there's the code to the complete FNRT algorithm, which is more efficient and more feasible to apply over a large area.